Hi everyone, welcome to Om Learning Lab. In this video, we are going to solve this problem which appeared in 2019 JEE Advanced, Paper 1, Mathematics section. The problem states, let S be the set of all complex numbers Z satisfying some condition which has been given. So they have given this particular condition, and if S is a set of all such complex numbers, they are talking about some complex number Z naught, which is such that some condition is given, its maximum of some set, then the principal argument of an expression is being asked for. Now, this problem is interesting for various reasons. The first reason is that a student needs to have very clear understanding of how complex numbers work. That's one. And the next point is, once a student is able to sketch out what has been mentioned in the problem, some basic intuition, some basic, ideas can be used to get the correct answer to the problem without solving it completely. And show you what I mean by that. Let's try to first sketch out what has been mentioned in the problem. So we can see that S is a set of complex numbers which satisfies this expression, Z minus 2 plus I. This is greater than or equal to square root of 5. Of course, I can rewrite this as Z minus 2 minus iota. This is greater than or equal to 5. Now, we know that this is the equation of circle because, the equation of circle is something like Z minus A is R, where A is a point in the argand plane and Z basically represents any complex number. So a set of complex numbers whose distance from a particular point is fixed, that's just circle, right? That's by definition, that's circle. That's how the locus of circle is defined. So if this is your A, this is your R, these are all your Z's. The distance is constant. So that's just from textbook definition of a circle. So we can sketch out this set S they are mentioning first to begin with. So how will S look like? So if this is my argand plane, let me draw that really quickly. So I'll draw a few points just so that everything is clear. So this is the real axis. This is real. This is imaginary. Again, textbook notations of how we work with argand plane. This is minus 1. This is minus 2. So on and so forth. 1, 2. Again, minus 1 and minus 2. Now, 2 minus 1. So 2 is on the x-axis. Minus 1 is basically negative on the y-axis. So if we have an expression A plus IB in complex numbers, A is the part which lies on the x-axis, the real axis. B lies on the imaginary axis. So this point is this, right? 2 comma minus 1. 2 on the x-axis, minus 1 on the y-axis. So distance from this point is greater than or equal to square root of 5. So if I try to sketch the circle here, it will be at a distance of square root of 5. Let me pick a different color at this point so that everything is clear. Square root of 5 is slightly more than 2 because square root of 4 is 2. So this is 1 unit distance, this is 2 unit distance. So it will be something slightly above here. So of course, when you are sketching something, it's always a good idea to look at the 4 directions and try to sketch accordingly. One interesting thing to note here is from origin is 0, 0. The distance of this particular point will be exactly square root of 5 because on x we have 2, on y we have 1. So the distance using Pythagoras theorem is square root of 5. So the circle will pass through the origin, and again distance is square root of 5. Let me just roughly sketch the circle now. And this is the point is here, so it will be 2 points down, 3 above 3 somewhere here. So let's just imagine the circle like this, right? And what they have mentioned is the set S is all those numbers which are satisfying greater than or equal to square root of 5. So the set that I am interested in is it includes all the points on the circle and outside it. So this is the set that I'm interested in. Please note that the points which lie on the circle are also important for this problem. Now that we have sketched the area that we are interested in to solve this problem, we'll go ahead. So we have defined our set S. S is basically all the points on this circle and all the points which are outside this circle from standard definition. We are interested in a complex number Z0 which satisfies some special condition. This Z0 maximizes this expression 1 upon modulus of Z minus 1. Now just think about it using basic concepts of algebra. You want to maximize 1 upon mod Z minus 1. If this expression is as high as possible, denominator should be as low as possible because the lesser the denominator, the fractional value goes up. So if this expression is more, Z minus 1 is less. So the goal is to reduce mod Z minus 1. What is mod Z minus 1? Distance from the point 1, 0. So this is my 1, 0. I want to reduce the distance from 1, 0. And which all points can I pick? I can pick points from the set S. S is basically the circle and the points around it. In other words, all they are asking is Z0 is a point from this set, this circle and points outside this circle, such that for this specific Z0, the distance from this point 1, 0 is as low as possible. Till here, that is what they mean to say. That in this given particular region, Z0 is that particular complex number for which distance from 1, 0 is as less as possible. So once we are able to find Z0, we can just plug that value in this expression and get our answer. More on that later, but the first part to understand here is how do I find that particular Z0 for which the distance from 1 is as low as possible. Now here I'll actually deviate a bit. I'll go to an additional idea. So this is a standard derived result actually, but I'll take the time to explain it in this video. So bear with me for a couple of minutes. So if I have a circle, right, this is the center. Let's say this is the radius R. And let's say I have a point P given here. And someone asks me, you know what, you find that point on the circle which is closest to P. Okay, you find that point on the circle which is closest to P. In fact, you know what, let me take a point P dash here. Okay, so let's find a point P dash which lies on this circle which is closest to P dash. Okay, so the idea is this P dash will always lie on the radius of the circle. So it will lie on one of the radius of the circle, and this radius, let's say this cuts the circle at some point C dash, then this P dash C dash, this distance is the least distance which will cut. I'll repeat it once again. If we have a point inside a circle and we are interested in finding a point on the circle which has the least distance to it, then draw a radius from the center of the circle passing through the given point. The point of intersection of this radius with the circle is that point on the circle which has the least distance. And this can be very easily proved as well. So we can prove using contradiction. By the way, just a quick note here. Of course, any point lying outside the circle will always be a suboptimal choice. Again, you can prove it using contradiction, because let's say someone is saying that, you know what, from P dash, this point outside the circle is the closest. Just join P dash to that point. You can always claim that this point which lies on the circle has a lesser value. That's obvious. So by contradiction, we can show that any point lying outside the circle is always a suboptimal choice. On the circle, this particular point passing through the radius will be the optimal choice. How? We can do a contradiction here also. So for the sake of contradiction, let me assume that there is a point called C double dash such that it's not on the same line, like the line joining the center of the circle and P dash, that particular radius cutting the circle, it's not that particular point. if I'm clearing that my claim is that P dash C double dash is less than to P dash to C dash. That's how contradiction proofs work, right? So all I need to do now is let's join P dash to C double dash. Let's join the center of the circle to C double dash and drop a perpendicular over here. Right. So I'm dropping a perpendicular here. What this will do is, please note, let's call this O. So OC dash is the radius of the circle R, which is same as OP dash plus P dash C dash, right? And since I dropped a perpendicular over here, using Pythagoras theorem, I can claim for sure that this particular part OP dash, let me call this particular part something like G. So using Pythagoras theorem on this particular triangle, please note, look at this part, OP dash is more than OG, that is the first thing, and P dash C double dash, please look at this particular triangle, will be more than GC. That's just basic application of Pythagoras theorem. If I just add both these sides, of course, OP dash plus P dash C double dash, this is more than OG plus GC double dash. My apologies, this is GC double dash, this particular triangle. So OG plus GC double dash is basically R. So this is more than R, and we know that R is what? OP dash plus P dash C dash from here. So this expression is more than OP dash plus P dash C double dash. This cuts off. So definitely P dash C double dash is more than, here we'll actually have a single dash from the previous expression. So this is actually more. That is to say, if I pick any other point other than this particular point, which is basically the intersection of the radius passing through P dash with the circle, that particular point will be a suboptimal choice. So that is the side note that I wanted to pass, but it's a very well-known property. I just wanted to show people how we can derive it. So you don't have to believe in anything blindly. In mathematics, everything can prove, of course. Now, coming back to the original problem at hand, let's use green for the remainder of the problem. So for this particular point then, of course, the point Z naught that we're interested in is, we'll join this point with the center of the circle and we'll extend it to cut the circle. So this particular point has to be Z naught. So this is my Z naught. Why this has to be Z naught, I just explained. And what's more, we can actually find the equation of this particular line, because this particular point is 2 minus 1 and this point is 1 comma 0. So if I use line equation y minus y1, let's call this as x1 y1, and let me call this x2 and y2. So if I use line equation, y minus y1 is m times x minus x1. So y1 is minus 1, so y plus 1 minus of minus 1 is m times x1 is 2, so x minus 2. M is basically the slope, so slope is y2 minus y1 divided by x2 minus x1, which will come out to be y2 minus y1, so 0 minus minus 1 plus 1 divided by x2 minus x1 minus 1, so this is minus 1. So this is minus x plus 2, taking the negatives. So on rearranging, we have x plus y equals to 1 is the right equation. Now, at this point, the question can be optimized. So till here, usually a normal student has to do the math till here. But from here, we can do some smart work and avoid more computations to just arrive at the result directly. What we can do, So from here, what you can actually do is you can, plug in the value of y as 1 minus x into this equation of the circle. You can find the equation of circle as well. You know the center, you know the radius. Find the equation of the circle, plug, replace, substitute one variable and get the exact value of z naught. But instead of doing that, we can actually make some observations. First, this line is x plus y equals to 1. So on y-axis, where will it cut? X is 0, so it will cut at 1. So 1 will actually be here. So if I extend this line, this will be 1. This is not my 1. 1 will actually be here. So this particular point z naught, let me take z naught as some a plus iota b and do the math here. So let's say z naught was a plus iota b. Can I make a few observations on z naught? So the first thing is this b. This is definitely more than 0. This is definitely less than 1. The reason is we know the equation of the line. And when x is 0, y is 1. And since this point, the intersection point lies in between, we are sure that this b will lie between 0 and 1. B is between 1 and 0. This is where correct sketching also comes into picture. You need to sketch as correctly as possible so that your results are more reliable. And coming to the real part, A, can I make a similar claim about A? Because here the line is cutting at 1, 0. And definitely the cut on the circle is between 0 and 1. So A also lies between 0 and 1. So this is the observation about z naught that we can make. And the expression that we are interested in is 4 minus z naught. So let's just simplify this. So it is 4 minus z naught plus z naught bar divided upon z naught minus z naught bar plus 2 iota. Is it right? Now if z naught is a plus iota b, z naught bar is the complement a minus iota b. So the addition of z and z naught is just 2a, 2 times the real part, known property. So this can be simplified to 4 minus 2 times a divided by. Similarly, z naught minus z naught bar. If we subtract z naught bar from z naught, you are going to get 2 iota b. So this is 2 iota b plus 2 iota. If I cut out 2, this will be 2 minus a divided by, so 2 is cut out, iota times b plus 1, something like that, right? Now, we have made observations that both a and b lie between 0 to 1. So this upper part, this is positive for sure. And this denominator that we are looking at, b plus 1, of course this is positive. So you have some positive expression, positive divided by positive for sure. And you have 1 upon iota. To normalize, multiply iota above and below. So it's iota above, iota into iota is minus iota. So it's negative of iota into this fraction which is overall positive. So it is negative of iota times some constant. Now we know exactly where negative times iota multiplied with some constant lies. If this is my argand plane, minus iota k, where k is positive, would look somewhere here. It will be on the imaginary axis on the negative side. And we are being asked its principal argument, which is definitely minus pi by 2. We compute angles in this fashion. So counterclockwise is positive, clockwise is negative. Here, this is minus pi by 2 for sure. Hence, this is the correct answer to the problem. Again, I'll be repeating the final part. Once we have sketched out the entire region using the standard definition of the circle in terms of complex numbers, and we have understood what is z naught. Z naught is the point such that distance from 1 is minimum, and we apply this particular property that I took some time apart and explained. And applying this property, we find out where z naught would lie. What we can do is we can find the line equation which will effectively cut the circle for us to find the z naught, find z naught. And then instead of completely finding Z0 and doing all the hectic math, we apply some common sense, which is that this point of intersection will be such that the real part and the imaginary part, both for Z0, will lie between 0 and 1. Once that is known, we start simplifying the given expression to get 4 minus 2 times the real part divided by 2 iota common b plus 1. Further simplification gives this expression, and we can observe that both numerator and denominator will remain positive. Multiply iota above and below, you will get something negative multiplied with iota. Iota is on the imaginary axis, something negative is on the, it's like this particular part on the argument plane, for which the argument is minus pi by 2. That would be the entire solution to the problem. The really beautiful problem, I would say, based on very fundamental concepts. You need to know how a circle is defined. The locus of a circle is defined using complex numbers. You need to sketch it out correctly. You need to find the set correctly. Then you need to find the point, and you need to use some common sense in order to get some idea about how Z0 would look like, and then finally get your required answer. So I would say, all in all, a great problem. I hope you got some idea about solving this problem. The explanation was clear to you. If you want to see more of such problems, such solutions from very scratch, very basic, without involving much formula and using absolute common sense, then do let me know in the comment section. If you like this video, consider liking, sharing, and subscribing to it. That's all for this video. Thanks. We'll meet in the next video. Bye.